Now let's see the concept of functional dependencies. We have already seen the concept of keys, isn't it? Candidate key, super key, like that. So what is a key in general? Given the value of that particular attribute, we should be able to identify a row in the table uniquely. So what I mean to say is, whenever you say that an attribute is a key, the actual meaning of that term is either candidate key or a super key. The meaning of that term is, given that particular, let us say this is A, and I'm saying that A is a candidate key, right? So given that value of A as, let us say, 2, you will be able to identify the other values. Let us say this one is A and this one is B, right? So given the value of capital A as 2, you will be able to find out the values of other attributes, right? That is the meaning of the key. So one way to write it is, given the value of A, you will be able to identify B and C, isn't it? So this is called as functional dependency. Got it? I'm just generalizing it, right? So in case, assume that so what is the meaning of formal definition is this: if I give any value of A, you will be able to uniquely say what are the values of B and C for that particular one. Which means if you say that A value is 2, then you will be able to say B and C are A and B, like this, right? So one way to define it is, if A dot, let us say, T1 of A, which means if a tuple T1 is having some value in the attribute A, and if it happens to be the same value for some other tuple, right, in A, then if this is the case, then for the tuple T1 and T2, B and C values should be same. This is the meaning of it. So what I mean to say is, in case if A is having some value in tuple T1 and some value in tuple T2, then A will have the same value. In case if these two values are equal, A will have the same value here. What I mean to say is, wherever if A repeats, I'm just taking it as an example, in case if A repeats, then B and C are also supposed to have the same value. That is the meaning of it, right? Or one other way to interpret it is, given a value of A, you should be able to determine what the values of B are, right? So it is not exactly the key. There is a kind of relationship between the key and the functional dependencies. If you want to understand it, let me take it this way. If I say A determines B, and if this is A and if this is B, then A need not be a key always, right? The meaning of it is, whatever is the value of A, you will be able to get a unique value of B, right? So it can be small a, small b, it can be 1 1 2 2, which means for every value of A, right, there will be a unique value for B. For every unique value of A, there will be unique value for B, which means for the value of small a, if you query about what is the value of B, you will always get 1, either here or here, right? That is the meaning of it. So A determines B means, given any value of A, you will be able to uniquely find out the value of B. Now why is it very important in terms of splitting the table, or let us say eliminating the redundancy is, see this, I'm just taking this example, see this. Now we know that given the value of A, you will be able to find out the value of B, isn't it? Then whenever A repeats, B is also repeating, right? Let us say A is repeating 100 times. Then what happens to B value? If A is repeating small a 100 times, B is also going to repeat small b equal to 100 times, which is completely a waste of space. So instead of this, what you got, I'm just taking an example. Let us say if A is having like this, A 1 1, and then maybe B, and then let us say 2, right? Or even 1 is also fine, right? Now what is the meaning of it? Whatever is the value of A, you will be given the value of A, you will always get a unique value of B. Then storing this value of B along with this is going to create all these redundant values, right? Instead of that, what we could do is, don't store, assume that C is having here D, E, F, G, H. Don't store B here, just delete it. You can save a lot of space. You can save B separately and you can write a new table AB, right? In this new table AB, you can write value of A is 1 and value of B is 2. That's it. So this entire information is not required. Just I can write it like this. In case if it is repeated 100 times, I have to just write it one time. So the main use of this functional dependency is, see what is functional dependency is, B is functionally dependent on A, or A determines B, or given a value of A, we can functionally determine what is the value of B. The advantage of this one is we can reduce the redundancy like this, right? So whenever you have such a relationship among various attributes, it is always better that you create a new table, right, in such a way that A will be able to determine B, right? So when is it useful? Whenever we are repeating lots of values, whenever there is lots of repetitions for A, right? So the main purpose is this: in a relation, let us say a very big relation is there, okay, and with lots of attributes, you have to find out some areas like that where there are lots of repetitions. And if you could let us say there is A and then 1 1 1 1, you have to identify all such spots in the tables and see that you can make it as a separate table with just A1. In order to identify this, functional dependencies are going to be useful. So functional dependencies will say what are such areas which could be minimized further, right? So using these functional dependencies, we can actually split the tables. It is also called as decomposition, right? So these are going to play a key role here, okay? Now what is that we are actually trying to do is, our final aim is to see that for every functional dependency, the left side of it, the attribute which is determining, is going to act as the primary key for a new table, right? That is called as BCNF. The ultimate aim is to make that for every functional dependency, I'll try to separate the tables in such a way that all the attributes which are determined by the left side are going to fall in one table, with left side being the key. That is the final aim, BCNF. Now in order to go to that final BCNF, I am going to go through various levels of normalization. So I am going to start normalization like this. One is called as first normal form. So we see that initially every table is in first normal form. We see that every table is in first normal form. From there we see that every table next is in second normal form. Then we see that third normal form, and then BCNF, right? So ultimately our aim is to reach BCNF. So in order to reach BCNF, we go through all these steps. In order to go through all these steps, we are going to use functional dependencies and candidate keys, okay? So there are various types of functional dependencies, like here I have shown you one example where left hand side is one attribute and right hand side is one attribute. Here you have seen left hand side is one attribute and right hand side is two attributes, right? So it can be, left hand side can be any subset of attributes and right hand side can be any subset of attributes, right? So in general, if you write x determines y like this, it is x determines y, not x tends to y, okay? Or not x derives y. The same symbol we might have seen it even in the grammars, right? There we say x derives y, but here x determines y. Given the value of x, you can uniquely determine the value of y. Now x and y can be a collection of attributes or the subset of attributes, okay? So x and y need not be single symbols. They can be like a b c here determines d e f, something like this, right? And now based on what does this x and what does this y contain, we are actually classifying these functional dependencies into three types like this. One is called as trivial functional dependency, and non-trivial functional dependencies, right? And the other one is semi non-trivial. What is trivial is, if like this, A determines A is trivial. Why? Given the value of A, finding the value of A is trivial, isn't it? So the meaning of this one is, I'll give you a value of A, you tell me the value of A, then what will I say? Whatever you give me, that is what I'm going to show you, isn't it? And the other one is, AB determines A. Given the value of AB, you will be able to say A. So these are useless, these are not at all useful, right? So this trivial definition falls under the category whenever X is a superset of Y, right? Which means whatever is present on the right hand side, if it is already present in the left hand side, then it is going to be a trivial dependency, and we are not really interested in trivial dependencies. And non-trivial dependency means, X and Y should not have any intersection part, right? For example, A determines B. Given a value of A, it gives the value of B. Or A determines BC, right? Or AB determines CD, something like this. So, whenever we give some information, we'll be able to know the new information. We are not interested in knowing the information which we already have, right? Like in this case. So, non-trivial functional dependencies are very useful, and we are really interested in them. And semi non-trivial dependencies are like this. Let us say xy derives yz, which means the intersection part is not phi, and moreover the left side is not a superset of right side, okay? Which means let's not use x and y, let me use some other notation. Let us say AB derives BC is a semi non-trivial, which means there is something in common. It is not completely deriving something new. So in order to formally define it, if you have x and y as the collection of attributes, then semi non-trivial means x intersection y is not equal to phi, which means there is something common between them, and moreover x